So welcome to the last presentation for this afternoon. This will be a talk by Professor Philippe Gachon. He is from the Department of Geography at the Université du Québec à Montréal. Professor Gachon, from 2003 to 2014, was the research scientist at Environment Canada on the Impact and Adaptation Research Division and at the Canadian Centre for Climate Modeling and Analysis. From 2017 to 2019, he held the Strategic Research Chair on hydro-meteorological risks related to climate change. Since 2019, he is the director of the ESCER Center on Regional Climate Analysis and Simulations here at UQAM. He currently leads as director a research network on floods in Quebec, the Quebec Intersectorial Flooding Network, which brings together 16 universities and more than 160 researchers across Quebec. His expertise includes regional climate modeling, storm and extreme analysis, regional climate scenario development, and risk of climate change disasters. So, Professor Gachon, if you please.
Thank you, Serge. Welcome, everybody. I hope that everybody is going well. Thank you. And we'll complement some thing also related to the talk of Jean-Pierre and also Patrick. The outline of my talk, I have 1 hour and I will keep for sure 15 minutes for question. Okay. I will first.
That's the way it should be.
Okay, good. I will first introduce some context and also basic concept related to climate forcing and driver, climate risk and scale, and also the impact of climate-related risk. An overview about the temperature change, especially since the beginning of the mid-19th century, and the key indicators and the anticipated change, but I will also focus on the risk associated with future climate change. And before to conclude, I will also briefly discuss how to reduce climate risk and their consequences, because they are huge, especially ongoing climate change has a strong implication on climate risk. Key basic concept first. What kind of element affect global viability and change? First, climate viability and change could be due to natural internal processes and also external forcing or persistent anthropogenic changes in the atmospheric composition or land use. We go to or classify all the internal processes of forcing, all processes related to climate system dynamics, could be natural or come cyclical or non-cyclical oscillation, come from both the change in the atmospheric dynamics and change in the oceanic circulation. And I will give you, after this, also an example of potential atmospheric dynamics and the change of this related to, for example, climate anomaly. All the external forcing, it's all processes or factors that are external to the climate system, could be due to, for example, the sun, solar cycle. There is some solar cycle, especially a cycle around 11 years, or volcanism from, for sure, natural external forcing. And they are classified as natural forcing, external forcing compared to anthropogenic forcing, for sure, come from the, for example, greenhouse gas emission. Now, to return to the context of the evolution of natural, for example, go to Anthropocene era, in which we are especially since the middle of the 19th century. You can see here on this figure, the top panel here, you can see the evolution of the concentration of CO2, the main atmospheric greenhouse gas that we have in the atmosphere, in ppmv, parties per million en volume. You can see here that there is a period in which we have high level of CO2 and certain period in which we have low level of CO2. And this corresponds, this high value of CO2 to warming interglacial period. And when we have low value of CO2 concentration, this corresponds to glacial period. And you can see here clearly that there is four main phases in which we have lower value of CO2 corresponding to 4 glacial period over the last 400,000 years. Okay. Now, if we return back again before this period, for example, an ice core comes from the Antarctic ice sheet, you can see also that there is, in the last 800,000 years, no value above 300 ppmv. Okay, close to 300 ppmv during, again, hot or warm period, and close to 180 ppmv during cold period. It's the reason why we can see clearly here in the last 100 years or 150 years, there is a huge amount, a strong increase in terms of CO2, completely unusual compared to the past 800,000 years. And this level of CO2 has never been observed in the last more than maybe 800,000 years, maybe before the Pleistocene period. An important aspect that we need to remember, and I will talk about this in my talk about the tipping point. The Greenland ice sheet has begun to develop around 2.6 million before present, as soon as the atmospheric CO2 was below 400 ppm. In other words, the Greenland ice sheet has never been able to develop before due to high value of CO2 and due to the fact that there is too warmer condition for the installation of the Greenland ice sheet. Now, if we go to the recent past, since, for example, after the Second War, we can see clearly that there is a strong increase, maybe close to exponential increase in terms of CO2 concentration in the atmosphere, especially due to the more and more consumption of fossil fuel, etc. And clearly, that's last December, we are above 410 ppm. In other words, above the threshold of 400, important for the not only constriction, but for the fact to preserve the Greenland ice sheet. In other words, we have multiplied by 1.5 the pre-industrial level of the CO2, a huge increase in the really short-term period. The important thing that you need to remember for this curve, it's the observation come from Mauna Loa Observatory in Hawaii. Red curve correspond to seasonal variation of CO2, and the black curve correspond to annual mean concentration. There is for sure seasonal variation due to the, for example, capture or the activity of the photosynthesis of the trees. In other words, normally in summer we have strong photosynthetic activity with lower amount of CO2 concentration in the atmosphere, and during winter, no trees, no photosynthetic, especially activity, especially in the northern hemisphere, means also higher concentration of CO2. Now, continue to the climate driver, briefly talk about the one example of a natural internal forcing. For example, the atmosphere circulation are sometimes affected by blocking pattern. Blocking pattern or atmospheric blocking means weather situation in which the normal zonal flow is temporarily suppressed in a sector by strong persistent meridional pipe flow. We have had recently some strong atmospheric blocking event in the North Atlantic. For example, here you can see in the figure here, it's for winter, spring, summer, and fall in the northern hemisphere. Green circle represent the area in which we have a strong value of blocking event. You can see clearly that there is a huge amount of blocking situation, especially over the North Atlantic and also over the North Pacific area, and also certain area in the Eurasiatic continent. And this has an effect on, for example, or could affect precipitation distribution and anomalies. Could be, for example, persistence of wet period in which we could have some flood event, or dry period in which this induce some drought condition. Atmospheric blocking also affect the temperature distribution, and the anomaly could affect the influence of the, for example, occurrence, duration, severity of heat wave, and also cold event. I have published a paper with my colleagues on this aspect because the atmospheric blocking, especially over the North Atlantic, has a strong effect on both the climate or meteorological condition over North America, but also over Europe. An example of this you can see here in the top left panel, the link, the correlation between the blocking occurrence in the North Atlantic and, for example, the geopotential high mid-troposphere. In other words, the atmosphere circulation as also is affected by this blocking. And you can see for sure a strong correlation with the pattern of positive and negative correlation over the North Atlantic, but also the atmospheric blocking occurring over North Atlantic affect also part of the feature of the atmospheric anomaly at mid-troposphere, also in the Eurasia continent. It's true for winter, but also it's true, for example, for fall. But also part of the summer condition is also affected by the atmospheric blocking occurrence over the North Atlantic. Another example here is the link between the blocking occurrence and the temperature, low-level air temperature. You can see clearly that the blocking affect part of the warm anomaly in the northeast of North America and part of the cold anomaly that you have also, for example, is in the south of North America, and also strong link also with the part of the cold anomaly in the northern area of Europe, but also warm anomaly about the Africa. The last panel here, bottom right panel, you can see here that there is also a link between the atmospheric blocking situation over the North Atlantic and the SST, sea surface temperature anomaly over both the Atlantic for sure, but also part of the anomaly, especially in summer, that we have over the Indian Ocean or part of the western part of the Pacific Ocean. Okay, in other words, the atmospheric circulation, the atmospheric blocking could affect not only local scale, regional scale situation over the oceanic area, but also part of the atmospheric circulation over this particular area, but also affect part of the anomaly across the globe. Now, the other important thing, but I will just briefly give you an example here, the Atlantic multi-decadal oscillation. The fact that the Atlantic has also a strong effect on not only the atmospheric circulation over the North Atlantic, but also affect part of the sea surface temperature anomaly across the globe. You can see here an example of if we just extract the anomaly only come from the SST anomaly, come from the Atlantic, without any removing the global mean SST anomaly, you can see clearly that there is a strong pattern of warm anomaly strongly affect the North Atlantic. And this recent results show that the Atlantic Ocean play a determining role in the multi-decadal variability of the global SST. Okay, these two kind of effect is also huge and could affect different range of climate variability at different scale. Now, another basic concept that I need to introduce the climate risk and also the scale. Risk, it's a combination of, for sure, the hazard, the atmospheric variability change, all the hazard affected by, for example, climate change, and I will talk about this in the following of my talk. But also risk is not only affected by hazard. The hazard occur over certain context of vulnerability and exposure. In other words, the risk is a combination of the hazard, vulnerability, and the exposure. And for sure, there is some action to reduce the hazard, as for example, reduce the greenhouse gas emission, but also reduce part of potential damaging effect of the hazard ecosystem, for example, base measure to reduce coastal flooding, if we talk about flooding, but also measure to reduce vulnerability related to social protection, livelihood, diversification, etc. The same thing for the reduction of exposure, coastal retreat, resettlement, risk-sensitive land use planning, etc., etc. In other words, risk is not only a problem of the climate change, is also a problem related to the context of vulnerability and exposure that the certain hazard has also, this has also an effect on the consequence of the risk related to the context of vulnerability and exposure. For example, the problem of scale also for the hazard and extreme. For example, if you go to North America, tornadoes, hail, extreme winds, snowstorm are strongly affected by local processes. In other words, we need to consider for sure the large scale, the blocking, for example, occurrence and also pattern of the SST anomaly. But we need also to resolve part of the local processes responsible for the occurrence, duration, and the intensity of these type of hazards. It's true also for the spring flood, especially in Quebec, strongly affected by regional or local scale feedback, flash flood, heat wave, but also extreme precipitation, and also forest fire. Forest fire that we have currently over the central part of the prairies is also strongly affected by the type of ecosystem, for example, lake, humid area, etc., etc. In other words, we need also to take into account certain scale related to occurrence of certain part of the extreme hazard at regional or local scale, considering high resolution model to be able to represent or to simulate this kind of event compared to, for example, large scale event could be also feasible to use a global climate model at core scale resolution to produce this kind of event. An example of this, we know that strong wind are strongly affected by topography, and we need to resolve this. For example, a grid scale, a global model, for example, at this kind of resolution, at 450 kilometer of resolution, do not represent not only the coastal land sea area, but also do not represent the topography that we have eastern part of North America. That we could, with a high resolution model, represent better, for example, the Richelieu River Valley, the St. Lawrence Valley, the area related to Charlevoix Mountain, because this has an effect on local scale wind over the St. Lawrence Valley, for example, but this also affects part of the strong value of precipitation that we have over topographic area. In other words, to be able to represent the certain hazard, we need also to develop a high resolution model to take into account this kind of event. Now, the impact. And it's a last basic concept that I would like to introduce. The risks, for sure, are quite complex and interconnected through various natural and human factors. I talk about this because the risk is a combination of hazard, vulnerability, and also exposure. It's not only a problem of natural or environmental system, it's also a problem of human condition or human factors. Hydro-meteorological hazards are caused directly or indirectly by climate change. And I will talk about this briefly in the following. And this leads to highest consequence on human and economic loss among all natural hazards. Strong majority of death and problem with health come from natural hazard, climate-related disaster. Okay, 79% of the all natural disaster cause a strong majority of economic loss, but also cause a strong majority of death across the globe. Not only also does climate change affect directly and indirectly population and society, it's also affect resiliency and also coping capacity according to the social context, sanitary factors, economic condition. It's really important to consider this factor also. In summary, climate risks are the result of dynamic interaction between meteorological hazard and climate extreme, and also pre-existing local vulnerability and exposure factor, which will notably affect socio-economic, technological, demographic characteristics of all society. An example of this, vulnerability factors are found on different kind of scale from both individual, community, and organizational level. Risk factors, for example, such as I have suggested, come from hazard, vulnerability, and exposure, but resilience factor also come from, for example, psychological resilience come from support, could be at social, community, and financial level, could be also capacity to deal with the stress, according to self-care, coping strategy, proactivity, and learning, and also meaning in terms of communication, engagement, and sense of community. All these disaster socio-ecological model adapted from shores is also important to consider because the disaster intensity, according to the affected population, come from also different kind of resilience factor, but also risk factor at different scale from both individual, community, and also organizational levels. Now, go to the temperature change and also go further to the effect come from this kind of change on different kind of risk across the globe. Everybody, I think, has seen this, but I'll briefly introduce the fact that since till the mid-19th century, the temperature at global scale, the annual mean temperature at global scale, are strongly increased, especially since 70s. The level of warming compared to pre-industrial period has reached a value of 1.2 degrees C. We go rapidly to the 1.5 degrees C that the Paris Agreement has used as a threshold and also do not pass over this kind of threshold, because we will see in the following that there is a huge amount of increase in terms of risk. For only Canada, especially since after the end of the Second War, Canada has warmed 2 times the rate of the warming at global scale, and 3 times the rate of the global warming, especially in the north, due to the polar amplification that I will talk about this briefly after. Now, per decades, we can see clearly that there is a strong increase. Again, decades per decades, we can see clearly that the last decades was clearly warmer compared to previous decades, etc., etc. And the last decades, it's the warmest on record since the mid of the 19th century, since the beginning of the historical record. Now, during that time, we can see at global scale that there is an increase, especially after the 70s, as soon as the rate of warming has accelerated. You can see that there is an increase in terms of natural disaster, mainly come from hydrological and also meteorological origin. In other words, there is no big change in terms of geophysical trends, especially volcano, earthquake. There is no trends. The only trends come from hydro-meteorological disaster. The direct consequence of the warming that we have observed in the last 4-5 decades. Now, 10 indicators of the warming world, the increase of sea surface temperature, such as I have also shown briefly about the North Atlantic, but also there is for sure an increase in terms of the temperature over the ocean and also over the land mass, an increase in terms of water vapor, a decrease in terms of sea ice, and I will talk about this briefly after, and also an increase in terms of temperature over the land, decrease of snow cover, glacier, and ice sheet. The rate of warming, especially over the last 3-4 decades, is not uniform across the globe. There is an area, especially in the north, where there is a higher rate of warming compared to southern area. For example, we talk about the warming trend in the Arctic. There is a strong warming amplification. A last report published last week by the AMAP, a group who give a regular overview about the ocean related to Arctic region, publish a report in which we can see clearly there is, especially for this period, 71 till 2019, a strong increase in terms of temperature trend, especially over the area here in the Barents Sea, Arctic region, but also north of Canada, especially Baffin Bay and also part of the Labrador Sea. And this warming is particularly huge in winter. Published paper in Nature suggesting in December, January, February, surface trend, especially for this particular area period, the strong increase that we have over the northeast of North America, but also over the Arctic region, confirming this type of trend that we have also recently observed over the Arctic region. Now, in terms of the impact of sea ice, clearly, for example, go to the left bottom panel here in blue. This is annual or seasonal sea ice. You can see clearly that there is a decrease in terms of annual sea ice from mid-80s till 2020. But the stronger decrease comes from the multi-year sea ice or perennial sea ice. more decrease for multi-year compared to annual seasonal sea ice. In other words, the extent of the Arctic sea ice in September, during the period in which we have the minimum sea ice concentration in the northern hemisphere, I decreased by 43% between 79 till 2019. Now, if we go to the, again, a figure come from the last AMAP report published last week, the strongest decrease come from the Greenland ice sheet here in the green curve. You can see clearly till especially 2000. You can see clearly the strong decrease in terms of the ice sheet come from the Greenland. For sure, there is also a strong decrease for the Alaska land ice, but the stronger decrease come from clearly the Greenland. Now, what could be the anticipated change and could be the effect related to the risk, occurrence, and also severity? Now, I'm pretty sure that also Jean-Pierre and also Patrick talk about this, but I will briefly summarize the main outcome come from the last IPCC report published in 2019 related to, it was a special report on the ocean and cryosphere in a changing climate. Alors, you can see here in the green curve, it's the RCP 2.6, the RCP scenario that we use as a target for the Paris Agreement. Okay, in other words, do not reach a certain level of CO2 and also start to decrease the CO2 concentration normally this particular decade. And the pessimistic scenario is the RCP 8.5. We do nothing. We continue to use fossil fuels and also continue to have a strong increase in terms of CO2 concentration in the atmosphere and also the other kind of greenhouse gas. And these two targets, optimistic, we go further to take action. We go also ratify not only the Paris Agreement, but we also go to action to follow the Paris Agreement. RCP 2.6 means by the end of the 21st century, we can keep the warming below 2 degrees C. And it's not the case for sure. For the RCP 8.5, we go to around 4 degrees C of warming compared to current condition. It's true for the global mean surface air temperature, but also low rate of warming above ocean, but also again a higher rate of warming for the RCP 8.5 compared to RCP 2.6. And this means also a huge effect for the oceanic condition. The pH represent also, as soon as we have high acidity value, you can see clearly that there is a strong decline in terms of biodiversity. All the coral reef will be strongly affected. It's true for pH, but also it's true for the oxygen within the oceanic column. Now, in terms again about the range and also pattern of the warming compared to for the two scenario, go on the right figure, you can see clearly that the rate of warming will be again higher in the northern part of the North Hemisphere, especially Arctic amplification effect, decrease of sea ice, more also heat contained in the oceanic Arctic Ocean. It's true also for higher rate of warming for North America and also Siberia. Now, for us, for Canada, North America, and also US, it's a combination of not only global climate model in that case, but regional climate model. we can see clearly that the rate of warming at global scale will be between 3.2 and 5.5. In the case of Canada, it will be between 5 and 10 degrees C for the RCP 8.5 scenario by the end of the 21st century. Huge rate of warming for our country. Now, for precipitation, this means by mid-21st century, an increase in terms of annual mean value of precipitation. This means also that around 20% of the increase in terms of total precipitation, and this increase also with a rate of warming by the end of the 21st century. We talk about for certain region, a rate of increase of precipitation by more than 30%. This could also induce some maybe difficulty, especially for flood, but also potential risk in terms of high value of intensity of precipitation. Now, risk associated with future climate change. An important aspect. It's one of the key figures that the IPCC has put forward in the last IPCC report, but also in the recent special report, the impact and risk associated with the reason of concern, for concern. I will explain a little bit about this kind of graph. Go to the first histogram here on the left of the figure. For unique and treated system, as soon as we go to a rate of warming, for example, at 1.5 degrees C of warming, global scale, you can see compared to current condition, an increase in terms of risk. We go, for example, from moderate to high, and could be very high value as soon as we go to 2 degrees C of warming. In other words, for certain particular system, this will strongly increase the risk and also potential damage. Now, for the extreme weather, as soon as we go to a certain rate of warming, we pass from moderate again to high value of risk related to, for example, to high intensity or high storm that we will have in the future related to higher warming condition. Now, the distribution of impact will also be affected by the rate of warming. Now, again, an important aspect, global aggregate impact, in other words, cascade effect. As soon as we go to 1.5 and maybe 2 degrees C or higher, we also go to moderate to high level of risk. And it's true also for large-scale singular events. And I will take 30 seconds to talk about this global aggregate impact. If the Greenland will disappear because we will not be able to decrease the CO2 emission, but also the CO2 concentration, the Greenland will disappear. It's a cascade, it's a tipping point related to no potential sufficient, snow cover in the Greenland ice sheet compared to the disappearance during the summer or warm season. In other words, the Greenland will disappear, will introduce between 4 and 7 meters of water within the oceanic area. In other words, this will have a huge amount of effect related to sea level. Okay? It's really a kind of tipping point that we do not want to see. Now, in terms of aggregate also impact risk for North America. Again, it's come from the IPCC report, the last assessment report. For the wildfire, for sure, there is, as soon as we go to 2 degrees C, a higher rate of risk compared to current condition, compared to present. And as soon as we go to, for example, RCP 8.5, 4 degrees C of warming, you can see clearly the huge amount of increase in terms of risk. We pass from moderate to very high risk at 4 degrees C compared to 2 degrees C and compared to present condition. And the dash area, it's a part of the risk that we could decrease with the adaptation. But again, with the kind of risk increase in the future, adaptation will be no able to reduce the rest of the increase in terms of risk. In other words, we could adapt, but after a certain amount of warming, we could also definitively be not able to adapt. We need to move, for example, for certain more safe area. Now, it's true for the wildfire here. It's true also for the extreme heat. In other words, hot spell, warm spell condition. We could also increase the rate of risk as soon as we go to a higher rate of warming. And it's true also for the flood. It's true for urban, but also coastal area with risk on health and the infrastructure for sure. We go, especially for the higher rate of warming, increase from moderate to a very high level of risk. In other words, to summarize, there is a strong increase in value risk when warming threshold will be above 2 degrees C. Now, risk associated with climate change, especially the hydrological cycle and the risk of flood and drought. Flood is important. It's an important, for sure, a natural disaster, but it's one of the disasters responsible for the higher rate of economic cost, but also higher rate of death. Now, with the warming, there will be a change in the intensity of precipitation. I talked about briefly before. Plant evaporation, evapotranspiration, for example, maybe higher rate of drying condition for plant and vegetation. Ocean surface and also depth condition, ocean circulation will be affected by different kind of change. Surface water runoff and water circulation in the soil will increase. Cryosphere, all the solid water within the Earth system will be strongly affected. Sea and continental ice will continue to decline. Snow cover, permafrost in the soil. Also, the intensity of low pressure system will be affected, and also maybe heavy rain or snow and strong wind will be also part of the result come from the warming condition. Frost and snow cycle, rain on snow event that we will have in the future, that we have had also in the recent past. Just to remind you about the summer condition with a huge amount of rain, especially in Montreal, but also in Quebec, in which we have also some flood in the middle of winter. Now, however, there will be substantial differences in change from one place to another, potential flooding in place, and regional drought elsewhere. Okay, it's the case currently in Quebec. We are faced with a big trouble with a persistent dry condition. Very few amount of rainfall since at least the beginning of March. It's a problem with the growing season, especially the agriculture will be strongly affected this year as soon as we do not have any sufficient rainfall over the following weeks. Now, another important aspect, especially related to compound and cascade effect, the warming will strongly affect the vector-borne disease come from, for example, warming in North America will be also a manner for certain vector-borne disease to spread northward with the maybe warmer condition. Warming and also climate variability will strongly affect epidemics and re-emergence of endemic disease. Certain also has started to begin to occur over, for example, British Columbia, but also over Quebec. And also for sure, warming plus introduction come from travel, such as for sure, definitely the pandemic period that we are currently. And climate change abroad also will introduce exotic vector and pathogen come from outside of Canada or North America. Now, how to reduce climate risk and their consequence before to conclude. Now, as put forward by the Global Risk Assessment Framework, the UNDRR, United Nations Disaster Risk Reduction. It's a strategy coordinated by the United Nations, especially the Sendai Protocol, has put forward different things that we need to do, especially related to the risk knowledge, governance of risk, and also transfer of risk, and also be better prepared. Now, it's an important consideration that we need to talk about and also to put forward. Such as I have mentioned, the risks are a combination of hazard, exposure, and vulnerability. And more studies clearly define different level of vulnerability, and also exposure from economic, for example, social, environmental, governance, legal, security. But also the skill is also more and more important from both global context, but also regional, national, subnational, metropolitan, local. We can see clearly for certain area in Montreal or certain person across Canada are not affected at the same level for the COVID compared to certain other area in which, for example, there is more facility, more also access to health system or health help, for example. Systems also from both human, ecological, economic, political, cultural, financial affect part of the risk, but also their consequence, especially at middle, but also at long term. In other words, we need to consider a global risk assessment framework to deal with more different kind of factors who affect not only risk, but also their consequence. Now, an interesting also message put forward by the last United Nations report published last December related to how the science could help to recover to maybe not normal, but to recover come from the pandemic era. Definitively, we need to pass from the reactive or destructive approach to a regenerative approach. We need to anticipate, to better prevent, to be better prepared, to also be able to recover in a better way, to build back better. In other words, we need to anticipate and not to react when we have crises. Because without any necessary facility for prevention, we will be more and more affected. And we'll talk about briefly just after about this systemic risk that we need to deal in the following decades. Now, this kind of innovative approach to pass from a reactive or destructive approach to a regenerative approach, it's come from the combination of the principle of integration and indivisibility that underpin the Sustainable Development Goals, plus the standard framework on disaster risk reduction. And these two approaches combine with maybe toward new innovation, mobilization, valorization of knowledge to improve, especially the prevention. Now, the other possibility to go to reduce the consequence is to not only adapt, but reduce the risk and different kind of risk factors. Exposure, vulnerability, transfer also the risk to public to private sector. For example, for flood in Canada, strong majority of risk are assumed by the public sector because we do not have insurance for flood. Only 6% of Canada people have an insurance to cover flood. In other words, strong majority are covered by the public sector. We need also to be better prepared to improve the intervention and the recovery, build back better. We need to take some lesson learned. We need also to transform the manner that we develop, but also we modify our environment, and for sure reduce the greenhouse gas emission, go to the transition of energy, and also increase the resilience with respect to new risk, especially not only resilience at organizational scale, but also community and also individual scale. Now, the risk property over the following decades will go more and more systemic risk emerging, because the failure infrastructure, financial crisis, food insecurity, species extinction, climate change, etc., with regard to the context, more hazards, especially climate-related hazards, more exposure with demographic increase, more vulnerability, especially related to aging population, will be another cocktail to improve the context in which we will have more risk and also more consequence. Driven by also hyper-connected financial system, increasing poverty, especially differences between rich and poor, who was strongly affected by the current pandemic, environmental degradation, poorly managed urban development, etc., etc. We need to consider that the risk will be more and more systemic in the future. It's the reason why we need also to consider to make some to develop some inter-sectorial approach to tackle multiple dimensions of risk. It's not only a problem of climate scientists. Now, in terms of conclusion, I have 2 minutes. Okay. Human activity has led to a change in the composition of the atmosphere. I have shown this with regard to the last glaciation phase, but also we have never seen this rate of warming and the current level of greenhouse gas emission in the atmosphere, maybe compared to Pleistocene or maybe a dinosaur era. And the increase was especially rapid and huge. It is very likely that human activities are responsible for more than half and maybe more. A recent studies by Zhu et al. Suggest more than 70% of the recent warming are directly affected by human activity, especially in the recent past. The change in temperature by the end of the 20th century is likely to exceed 1.5, maybe 2, especially if Paris Agreement to reduce greenhouse gas is not followed by action. Warming will continue beyond the end of the 21st century. The time that the CO2 will continue to be there in the atmosphere, but also to be there in the oceanic area, with high interannual and decanal variability from both the atmospheric and oceanic forcing, such as I discussed briefly. Certain atmospheric forcing and circulation will also exacerbate this kind of change and the rate of warming. For example, El Nino, Atlantic multidecadal oscillation, will strongly affect the rate of warming that we'll have around North America, but also Europe. And also, the warming is not uniform with strong regional variability. Canada and Quebec, warming higher than in other continents of the Northern Hemisphere, with a rate 2 to 3 times higher, especially in winter, and higher in the north compared to the south. Tipping point. The past is no longer a guarantee of the future. We have never seen not only the rate of CO2 concentration, but were a rate of warming above 1.5, we have no reference. The Holocene period 6,000 years ago was around 1.2, 1.5 warmer compared to the 19th century. Will be higher as soon as we go to higher rate of CO2 concentration. The impact will be measured on intensity, especially at subdaily scale and type of precipitation. There is high uncertainty, Patrick has talked about this, at local scale, but there is, again, more and more convergence of kind of result at this kind of scale with higher resolution model. Occurrence of rain and snow, thawing or fast thawing period, especially flood in 2017 in Quebec, was partly due to this kind of high thawing period, but also very rapid thawing period with a huge amount of precipitation above snow cover. Freezing thaw cycle will be strongly affected. Greenland ice sheet and multi-year sea ice. Multi-year sea ice could disappear, especially by mid-2035. The last estimation suggests that in the following 14 years, maybe no more multi-year sea ice over the Arctic region in summer. Main issue and needs. We need very high resolution model grid to resolve hydro-meteorological hazard and climate extreme from different kind of processes. It's true for thunderstorm, it's true for snowpack thawing and also mountain and valley winds. We talk about this with Hydro-Quebec because more and more concern are related also to strong rain because this strongly affects the distribution of electricity in Quebec. Now we need to develop intersectorial research and approach, including combined social and health science, to increase also research collaboration between climate scientists and social environmental specialists, especially to improve the vigilance related to high impact weather event, but also to better manage systemic risk. Now, in terms of risk of heat wave, intense rainfall, flood, drought, with wet, dry, persistent, and intense synoptic storm with more atypical trajectory are expected to increase in the future. For sure, the uncertainty remains high at regional or local level, but we need to better quantify this kind of risk at a local scale. Now, in developing country, vulnerability to this natural hazard is high, where by necessity, the poor people tend to occupy the most exposed area. And also it's true in Canada, in North America. go to the current crisis in terms of location for people, you will see that there is some area in Montreal in which you have higher risk as soon as you to go to a certain area of Montreal in which we have the poor people who live there. Now, in developed countries such as in Canada, vulnerability increases with economic growth. Social inequality and dependence on new technology, aging population, accumulation of assets in the drought-prone area are also factors who also increase the exposure. The last part of my conclusion. Now, to identify the risk associated with the hydro-meteorological hazard in a changing climate, we need developing innovative approach. The past is no longer a guarantee of the future. We need to combine the change in weather variables come from different kind of scenario, a joint occurrence of duration, intensity, and also with a combination of the exposure, sensitivity, and vulnerability of the environment. We need to improve the knowledge of the physical processes and human functioning and their interrelationship. We need also to develop multidimensional understanding of risk, the importance of cross-sectoriality in risk management and resilience development. It's a key issue put forward by United Nations also. Transforming the way we do business, evolving on know-how and know to do, including value system, regulatory, legislative, administrative framework, financial institution, technological and biological system, learning and relearning how to live better together and with our environment while protecting it to better protect us is probability part of the solution. That's it.
Thank you so much, Philippe Gachon, for this very interesting and very informative lecture.